A hearty welcome to all those who have joined us this evening. Myself, Dr. Prema, Associate Professor at BMS College of Engineering, Bangalore, and Treasurer of IEEE PELS Bangalore chapter. It's my privilege to host today's webinar on future grid integration of renewables, jointly organized by BMSC, IEEE PELS, and IES Bangalore chapter, on the occasion of PELS Day 2021. I'm very happy to introduce today's speakers, Dr. Kaushik Basu, Associate Professor at the Indian Institute of Science, Bangalore, and Dr. Anirban Pal, Postdoctoral Fellow at the University of Nottingham, UK. Dr. Kaushik Basu received the BE degree from Bengal Engineering and Science University, Shibpur, India in 2003, MS degree in Electrical Engineering from Indian Institute of Science, Bangalore in 2005, and PhD degree in Electrical Engineering from University of Minnesota in 2012. And Dr. Basu was a design engineer with Coalbat India in 2006 and an electronics and control engineer with Dynapower Corporation USA from 2013 to 15. Currently, he is an associate professor in the Department of Electrical Engineering in Indian Institute of Science. He has been an author and co-author of several technical papers published in peer-reviewed journals and conferences. His research interests include various aspects of general area of power electronics. He is an IEEE senior member and the founding chair of both IEEE PELS and IES Bangalore chapters. Anirban Pal received BA degree from Indian Institute of Science and Technology, Shibpur, India in 2010, MA degree and PhD from Indian Institute of Science, Bangalore in 2015 and 2020 respectively, all in electrical engineering. He is currently a postdoctoral research fellow with the University of Nottingham, UK. From 2010 to 2013, he worked as an assistant manager in National Thermal Power Corporation Limited. His research interests include high-frequency link inverters, dual-active bridge converters, resonant converters, source switching techniques, design of high-frequency magnetics. So that's about the speakers. I have a few instructions to participants. The participants can post their questions in the Q&A section. The questions will be taken up at the end of the webinar. And make sure that you're giving your name also while posting the question. Sir, shall we start the event?
Yes, madam. I think
yes.
We can start, and I'll try to share my screen, right?
Yes, sure.
Is my screen visible, madam?
Yes, sir, it's visible.
Okay. So very good evening, good afternoon, and good morning from wherever you are joining. And I would really like to thank Prema madam for her kind introduction. And we'll start the talk. So today, so I am Kaushik, and the first part of the talk will be delivered by me, and the rest Anirban will do. So the title of our talk today is the future grid integration of utility scale renewables. Ma'am, my screen is visible and the voice is clear? Ma'am, my voice is clear?
Yeah, it's clear. Yeah, it's clear.
Okay, okay, okay. Thank you. So in this talk, first we will review the state-of-the-art solutions for grid integration of utility scale renewables. Now, by utility scale, we mean large amount of power in the order of several megawatts. Typically, this type of units is connected to the transmission grid, like the large fossil fuel or nuclear-based generating stations. Now, this slide shows how large solar farms are connected to the grid. Several solar cells are connected in series and parallel combination. And at a given irradiation, the available active power, P, is a function of the terminal voltage. there is a particular voltage at which the available power is maximum. So a three-phase DC to AC converter is employed to connect this solar field to the grid. This is also known as the two-level three-phase regular inverter. Now, this inverter is controlled in rectifier mode so that the voltage at this port can be adjusted to this particular voltage so that we can extract and push the maximum power into the grid. Now, as the day goes by, the solar irradiation will change, and this voltage at which you get the maximum power will also keep changing. And the DC to AC converter will keep adjusting this voltage so that we can keep extracting the available maximum power. And this is what is called the maximum power point tracking. The typical voltage range of the solar field is in 700 to 800 volts. A 50 hertz transformer, or what we call a line frequency transformer, LFT, is used to connect the output of the inverter to the AC grid. And here we are talking about a 400 volt low voltage AC grid. Now, why is this line frequency or 50 hertz transformer is needed? Actually, there is a strong parasitic coupling between the solar cell terminals and the ground. This results in the flow of unwanted circulating or leakage currents, resulting in conducted electromagnetic interference or EMC, spurious tripping of the inverter, and power loss. Now, a transformer can break the path of this current flow. Now, each unit that you are seeing here is typically rated at 350 to 500 kilowatt. So many such units are paralleled to support a 10 to 20 megawatt solar field. Now, a transformer isolation also helps in limiting circulating currents among the parallel units. Besides this, transformer also provides the galvanic isolation required for safety, and also it helps in voltage matching, right? You can see that as the DC port voltage will change with rain and shine, and the AC grid voltage will also fluctuate. And the maximum gain of this DC to AC three-phase inverter is limited. So you need something to match the voltage. Now, this slide shows how the energy from wind is pushed into the grid. Now, a wind turbine is connected to an electric generator, which converts the mechanical energy into the electrical one. Now, a permanent magnet synchronous generator, PMSG, has a smaller size because of the use of permanent magnets in it, and has a lower maintenance due to the absence of brushes and slip links in the rotor when compared with a traditional generator with field windings in the rotor. Now, again, similar to the solar case, the available active power now for a given wind speed is a function of the generator speed. The grid side AC-DC converter is controlled to achieve a particular rotor speed so that you can extract the maximum power available in the wind at that particular wind speed. And as the wind power changes, the speed is also changed so that the maximum power can be tracked. The grid side DC-AC converter is again controlled like the solar case in the rectifier mode to maintain the intermediate DC link voltage. And again, you note that it's a very similar case with the solar. So we have a line frequency or a 50 hertz or 60 hertz transformer in between the DC-AC converter and the grid. You may be wondering that why I'm talking about PMSG based generation. Many of you have heard about DFIG based generation. So DFIG stands for the doubly fed induction generators, which are certainly common today. And unlike regular induction machines, it has both stator and rotor circuits are excited. And that is why the name doubly fed. DFIGs are interesting because the power converters are used to control the rotor circuit and hence has a lower power rating. But the trend is the industry is slowly moving from DFIG to a PMSG based generation because of lower size, because of the permanent magnet, and DFIGs has higher maintenance needed due to the presence of brush and slip rings. So now I would like you to see that in both the solar and the wind, you have seen this structure, a DC to AC converter, DC to three-phase inverter, three-phase AC inverter, is connected to AC grid through a line frequency transformer. And in both of these cases, the active power flow is unidirectional. You never push active power into the solar field or into the wind turbine, right? And now you see, and I told you that why we need this 50 hertz transformer or a 60 hertz transformer. Now this line frequency transformer turns out to be the most expensive, the largest, and the heaviest component in the entire power converter system. Now the operating frequency of this transformer is inversely proportional to its size. So if we can increase the operating frequency, we can reduce its size. So here you see a picture that Professor Mohan was kind enough to share with me. And this work was actually done some time back in Los Alamos National Lab, where a similarly rated transformer is designed. Here is a 60 hertz transformer and a similarly rated a 20 kilohertz transformer. You see the reduction in the weight goes from 35 tons to 450 pounds. So this is like 150 times lighter. And I think they have used this advanced fine met material here. So the losses also went down by 10 times. So there is a magic. So if you can increase the frequency, you can reduce the size. I think one of the main idea of using power electronics is increasing the frequency and reducing the size of the passive components, right? So that drives the development. But at the same time, I would also like you to note that this conventional system with the DC-AC inverter and the line frequency transformer is actually highly efficient. If you go by IGBT-based design, right, at the peak power, you can design a converter, say at 350 kilowatt or a 500 kilowatt, which has an efficiency in the ballpark of 98%. And this line frequency or 50 hertz transformers are around for over 100 years. And we have done a lot of work on this. And now the efficiency stands for close to 99%. So you can see that combined, this system has a very high efficiency of 97%. Actually, if you use silicon carbide, you can even push this to 98%. Now, then how can we replace this line frequency transformer into a high frequency transformer, right? So here is a possible solution where you can actually use an isolated DC-DC converter, which incorporates a high frequency transformer in it, followed by a DC-AC inverter connected through a DC link. Now, this solution has not become interesting, though it is around for a long time and used in many, many other places for this kind of high power applications, right? And I'll tell you why. Because this interstage DC link has to be maintained, and we have to put a large capacitance, and which is typically an electrolytic capacitor needs to be used. And these electrolytic capacitors are the least reliable component in the entire power conversion system. And also you see that now before I had just one DC-AC converter, but now I am adding another converter, right? So I have higher complexity. I have many more semiconductor devices or switches here, right? And also in this case, the DC-AC, like the previous case, is hard switched. But this DC-DC converter can be soft switched. And I will discuss more about hard and soft switching soon in a later slide. Now, if you look at the efficiency of this type of system, I already told you that this DC-AC inverter will be somewhere around 98%, considering you are using IGBT-based design. And this DC-DC converter, again, considering IGBT-based design at a ballpark of 100 kilowatt, right? You can achieve a peak efficiency of around 97%. Now, you may be wondering that why the efficiency is a little low here, because you have a transformer here inside. Don't forget that, right? So if it is 97%, this is 98%, the best you can do is probably 95%, right? So that's not good, because the original system that we wanted to replace was 97% efficient, and 2% efficiency at megawatt scale, that's a lot of power. So now this slide shows that how large-scale fuel cell-based systems can be integrated to the grid, right? And here we actually use the similar solution that I just discussed, an isolated DC-DC followed by a DC-AC converter. And here this line frequency transformer is optional because you already have galvanic isolation here that will give you safety. But sometimes LFTs are required in order to do voltage matching, right? You see here a 300 kilowatt system, but mind you that you cannot build a 500 megawatt system like this. You have to put a lot of these systems at a lower power and parallel them. So now let us take a closer look at this conventional solution, right? So I told you that we have a DC-DC converter followed by a DC-AC inverter, right? So let us just see that how it works, right? So you see this DC-AC converter is an H bridge. This is, we call it H bridge. And if you take this DC link voltage is a DC flat voltage, then if you turn on this to diagonal switches across the AC port, this is what we call the AC port, you will apply a positive voltage like this, right? And if you turn on the other two devices in the opposite diagonal, you will apply a negative voltage, right? And if you turn on the top two or the bottom two devices, you will be shorting this output terminal, and thereby you will applying a zero voltage. So now you can actually, by controlling this bridge, you can generate a voltage, pulsating voltage waveform like this across this terminal. And you see what we are doing here, we are just varying the width of these pulses, right, sinusoidally. And this is what is called a pulse width modulation, right, a PWM, right? So now you can vary this pulses sinusoidally, and that will result in a sinusoidal voltage waveform. So if you look at this pulsating voltage waveform, it will have this dotted blue sinusoidal voltage waveform, which is at 50 hertz, along with some high frequency components, which could be knocked out by this line filter inductor, right? So the current here will be beautiful sinusoid. Now let us take, and remember, every time the switching happens here, see, so many times there will be switching happening over a 50 hertz cycle, there will be loss in this converter. Now let us take a closer look at this DC-DC converter. This is also known as the phase shifted full bridge DC-DC converter. And what happens here, I told you that like this, here also you see another H bridge, right? So this H bridge will actually can generate a waveform like this. So I call this waveform the quasi square wave waveform. This will be at a high frequency, about 20 kilohertz, right? And it is a purely AC waveform. And this is not a perfect square wave because you have duty cycle modulation here, right? And you know that I can, through this bridge, get positive, zero, and negative, right? So you get this quasi-square high frequency waveform, which can be passed through this high frequency transformer here. And this diode bridge can rectify this to the unipolar pulses, duty cycle modulated unipolar pulses, and which will have an average value along with the high frequency components, which can be knocked down by this LC filter. So the thing is that only the average of this waveform will appear across this bus, right? Which will be used to invert here by this inverter. Now the thing is that this is very much like your buck converter. This is essentially the principle of buck converter, right? So now using the parasitic inductances of the transformer and these parasitic capacitances, it is possible to make this converter switch soft. That means there will be no losses in this converter, right? Switching losses in this converter. But this inverter is always hard switched. Again, I will explain you in more detail what I mean by soft and hard switched. Now, here is a better solution. Now you see what I have done. I have just removed that inductor and capacitor in this link, right? And I made just one total converter. And how we will control this? Now, I already told you with this DC side bridge, I can make a quasi-square waveform. Now, how about I start varying the pulse width of this quasi-square waveform sinusoidally, right? I will get a waveform something like this, which has a high frequency AC, right? And that we can pass through this high frequency transformer. And then you have this diode bridge, which will convert it to a train of unipolar pulses. But now, unlike the previous case, the pulses will be varying sinusoidally. The width of the pulses will be varying sinusoidally, right? So you have something like a rectified AC here. And then we have this output bridge, which we can use to unfold it and get the PWM waveform like we got in the previous slide, which will have a nice, beautiful sinusoid in it, right? And notice here that when you are in the positive half of the cycle, you can just simply turn on these two red switches. And when you are in the negative half of the cycle, you are turning on these two blue switches, right? So this converter, the DC-AC converter now is switching only twice in the line frequency cycle. So effectively, the switching loss, because you are not switching that often here, the switching loss is becoming close to zero. And this is what we call line frequency unfolding. And also in this bridge, you can still get soft switching as we have seen in the phase shift full bridge converter. And this diode bridge, if you use good diodes, there is no reverse recovery. So there will be no switching losses here. But of course, there will be conduction losses, right? So here is a solution which does not use the inductor and the capacitor in the link, and there is no electrolytic capacitor here, so it is better. Reliability is better here, and you are getting total soft and line frequency switching. The switching losses are becoming close to zero in this converter, so it has a better efficiency. Right? So you can see here, this is not a two-stage like a DC-DC and DC-AC. So that's why the name is single stage. So directly we are converting the DC into a pulse width modulated AC at the output, right? So now this idea is not new. This is known for a very long time. I think the first paper that can be traced is Professor Ranganathan's. I think he did his PhD work with Professor Ziogas from 1983. We can see this paper where they had this idea that with an H bridge from a DC, they will make high frequency AC, then they'll pass it through a transformer and a tank circuit. And then there is a converter here that you can see, which will change the line, the high frequency AC. It's a cycloconverter, right? Which will turn the high frequency AC to a low frequency AC here, right? Though they did this work based on a resonant tank, but this idea is very similar. Now, Professor B.K. Bose did some work very similar to this from 1985, and then Professor Sudeep Majumdar from IISc did a lot of work on this kind of topology with unidirectional and diode bridge around 2010. But this exact converter appears in one of our earlier papers from 2015. So now you can see that, remember in the grid scale, there is a three-phase, right? We don't have single phase like we have seen in the previous circuit. So you can actually connect three such single phase units and intelligently connect the output, like we are making one output and making a neutral, and others we are connecting to this three-phase grid. We can still generate the three-phase AC by modulating this three H bridges. Remember, now the modulation or the pulse width modulation is happening here in this bridges. So this bridge will modulate and give you phase A voltage. This will give you phase B voltage, and this will give you phase C voltage. And another very interesting thing that happens here is the blocking voltage rating of these devices. The blocking voltage is the voltage that the device will be blocking when it is off, right? So that becomes here equal to the peak of the line to neutral grid voltage, right? But for a conventional converter, like the DC-ACs that we have seen in the state-of-the-art solution, the blocking voltage is close to twice, right? So why we are worried about blocking voltage? Because one thing is that if you reduce the blocking voltage, of course, the cost of the switches will drop. And also, as the blocking voltage reduces, the on-state drop or the conduction loss of the devices will also reduce. So now we have, but you see this solution has too many devices. It is complex converter, right? So then can we reduce the number of devices? Yes, we can. So here is one solution. See, the DC side bridges are still remaining the same, but AC side, we had a full bridge and now we have a half bridge, but we still have 4 diodes here in every phase. And you can see here what we are doing here. We have now 2 windings. So this is, if you know a little bit of power electronics, this is the famous push-pull configuration. So when you are in the positive half or in the red part of the grid line, so then you will be basically rectifying with these 2 diodes and this switch will be on. And when you are in the negative half, then this blue devices will be working. And again, these half bridges are line frequency switched, incurring very limited loss. And you have your the diodes are basically doing the rectification here. But here, the flip side is now we have 2 windings here, and also we have the blocking voltage of these devices are twice the anti-neutral peak. But I would like to also mention that in the previous case, we had a full bridge here and a full bridge here. So every time there were 4 devices, 2 diodes and the 2 switches were in the path of conduction, right? But now here you have always 1 diode and 1 switch is in the path of conduction. So that will also result in a little bit of a lower conduction loss, even though the blocking voltage has gone up. So now let us look at this issue of soft switching. Now, this part may become a little bit difficult. We will go a little slowly and try to let you understand this concept, right? So now what is about this switching loss, hard switching and soft switching, right? So look, this is a device, right? So this is the current through the device and this is the voltage across this device, right? So when the switch is on, yeah, there is a non-zero current flowing through the device and the voltage across the device is very low. It's close to 0. It is not actually 0. And that is why you get conduction loss. And when the switch is off, then the current through the switch is 0. But the voltage of the switch is the blocking voltage. So it is the voltage based on the circuit it is connected to, right? So both in the on and the off state, because the VI product is close to 0, there is no loss in the switch. But when the switch makes a transition between on to off or off to on, like here it is on to off, then the voltage across the device will have a voltage and current across the device will have a non-zero overlap, right? And that is what we see, that there is a bump in the VI product, and this results in a loss in the device. And this is the switching loss, right? This is the switching energy. And more you switch, more frequently you switch, more you get the switching loss, right? So now what can we do about it, right? So this is a problem, right? So what can you do about it? So what you do is you do something in the circuit so that only during turn off, mind you, it does not happen for turn on, only during turn off, you try to slow down the rise of the voltage across the switch, right? So what happens is your current then quickly falls to 0, but the voltage is slowly rising. So when the current is still falling, the voltage is close to 0. So that will make the bump in the VI curve very small. And this is the so-called zero voltage switching, or the ZVS. If you are familiar with power electronics, you heard this term, ZVS, right? So now in our converter, we are trying to achieve this GVS, and I'll tell you what is going on here, right? So again, this is a complex discussion, and I do not expect that you will get fully about this, right? I may teach this in few classes in a course, right? But let us slowly go, and I believe it is possible if you it is possible to understand, right? So let us try, right? So this is our one phase of our converter, right? That just we have seen, right? And I told you by controlling this H bridge, we are applying a quasi-square waveform, like this blue waveform here across this bus, whose duty cycle we are changing sinusoidally, right? And let us look at the situation when we were applying zero voltage across this XY terminal or across this transformer, and we are here. And we are going to study the transition to a negative voltage, right? Transition to a negative voltage. So now let us see what is happening when the zero voltage is applied. So when the zero voltage is applied, you have this switch turned on and this diode is conducting. So this diode is just short. So this Y pole voltage is VDC here. And the X pole voltage is also VDC because the switch is on. So across this, you have a zero voltage here. And because the current is positive, right? We are on the positive half of the current, right? Because of the current is positive, this diode D1 is conducting and this switch is on, right? So this is the state we are in. And now what I'm going to do is like here, I'm going to turn off the switch S, right? And also notice I have some capacitor across this switch. So now, okay, so now to slow down the voltage rise across this, so that I can get across the device, so that I can get GVS, right? What I am doing here is I am adding external capacitance. Now, how much external capacitance one needs to put so that you get GVS, right? And whether the parasitic output capacitances of the device is enough, right? It's a complicated question and it requires a good understanding of the switching dynamics of the devices. We tried to answer this question in one of our recent work. If you're interested, you can take a look. It just came out a few weeks back, but this is in the context of silicon carbide MOSFET though. So now I have turned off the switch S, and now let's see what is happening here. See, across this, because the switch was conducting, across this capacitor is charged to zero voltage. And this capacitor is charged to VDC because the voltage across this plus this has to be the receiver's voltage, right? So now, if these capacitances are not there, and you have an inductive current here, right? If these capacitances are not there, if this switch you turned off, then the current typically flows through this diode. That is happens in all other converters, right? If you don't put this capacitor. But look, the capacitor here across this diode is charged to be DC. So this is reverse biased. So the current cannot go to this diode, right? So the current has to now both of these devices are off. Current cannot flow through this diode because it is in opposite direction. This diode is reverse bias. So the current here, the primary current IP here can flow only through these two capacitors, right? And now let us look what will happen if the current starts flowing through these capacitors. Remember, this capacitor was at zero voltage, this capacitor was at the VDC voltage, right? And remember, this diode is conducting, so this point is at VDC voltage. Now, if the current starts flowing through these capacitors, right, this capacitor will start discharging, and this voltage will start going down. This voltage will, of course, will start to build up. Now, what will happen to this voltage, X voltage? It will start becoming less than the receiver's voltage, right? So what will happen to the XY voltage? It will start becoming negative because Y is still at VDC, X is falling from VDC. So it will become negative. So if it becomes negative, look, if this diode is conducting, here the voltage is negative, here also the voltage will become negative. So across this diode, the voltage will start becoming negative. So if the voltage becomes negative across this diode, it will forward bias this diode D2. And if it forward biases diode D2, it will basically D1 and D2 will short this transformer winding, right? And so that means effectively this part will become electrically shorted. So that is what I'm showing here. This is an equivalent circuit of this particular state of this circuit, right? So now you have these two capacitors and this leakage, this is the leakage inductance of the transformer, that is L, and these two capacitors are those two capacitors that we have added to get soft switching. And this is the pole X, right? And now this diode is not conducting because across this voltage is VDC, so this diode is reverse biased. So that means now you see that you have got yourself a LC tank circuit, right? And starting with some initial condition, right? And if you have studied a little bit of electrical engineering, you know an LC circuit like this will start oscillating sinusoidally. That means the current through this inductor and the voltage across this capacitor will start changing sinusoidally. And that is what will happen here. So you see this blue is the current through this inductor, which will start falling sinusoidally. And this red is the voltage across this capacitor, which will start increasing sinusoidally. So now what will happen is that this voltage will start rising, right? And the moment this voltage reaches the DC bus voltage, this voltage across this capacitor will become zero because the sum of these two voltages is zero, right? So if that happens, then what will happen? This diode will get forward biased now, right? And this process will stop at this point. And once this diode gets forward biased, right, this voltage across this device will become zero and the current will actually start falling linearly, right? Because now no capacitor is there in your circuit, it is only the L dynamics, right? And now you can actually turn on this switch, right? And the turning on of this switch, because it is not carrying any current, it is the voltage across it is zero because the diode is conducting, it will be a soft turn on. But look, the peak of this red voltage is this value, right? I naught, whatever the value of this current into root over L by 2C, right? So now what happens is that if this DC bus voltage is more than this, then this process will not happen and the current will become negative. And that if the current becomes negative and this voltage will now start falling, it has never reached the DC bus, this diode will never click in. And if diode is never clicks in, we cannot get the GVS turn on of this switch, GCS turn on, what we call for this switch. So we will lose the soft switching, right? So that means always this DC bus voltage should be less than this. So that means you should have this, and that means the load current should be always greater than this number, VDC by Z naught, right? So this is a fixed number here based on the circuit ALC values and VDC. So that means if your load current becomes lower than this value, you are not going to get soft switching. So now if we look at our circuit that we are talking about, right, this current here, actually a sinusoidal AC current, right? So near the zero crossing, it will fall below this limit that we just talked about. And this is the places you're going to get hard switching. You are not going to get soft switching and your losses are going to increase. And also you see that we have too many switches here. We have 4 switches here, 2 switches here. So 6 switches in every phase and 3 phases. So you have 12 devices. So now what we can do? So now I'll give it to Anirban and he will continue from here. Anirban, you can start sharing your screen.
Thank you, Professor. Am I audible now?
Yes, I will.
Sir, I think you have to take out. Yes, thank you. Is my screen is visible? Hello?
Yes.
Okay, thank you. So as you have seen in our previous topology that we have in the DC side converter, we have 3 edge bridges. These 3 edge bridges are modulated to generate pulse width modulated quasi square wave across the transformer primary windings. The pulse width modulated quasi square wave are shown here. As you can see, VA for phase A, for phase B is VB, and similarly we will have for phase C. Now if we consider a half bridge leg as shown here, the 2 switches are complementary switched. The gating pulse of each of these switches are a square wave with 50% duty cycle. Now let us consider the case for phase A. We want to generate a voltage VA like a high frequency quasi square wave. How can we do that? So if we consider this red leg, the switch SA3 has a gating signal like this, which is phase shifted with respect to switch SA1 as shown here, and that phase shift is MA TS by 2. This particular switching strategy will effectively apply a quasi square wave. Similar process we can do for phase B, where the green leg top switch SB3 is phase shifted with respect to SB1 by MB TS by 2. Now here I want to mention that MA and MB are sinusoidally varying modulation signals as shown here in red and green color. For phase C, similar process can be repeated and we can generate thus the quasi-square wave high frequency AC across the transformers. Here, if you carefully notice, you can see the switch SA1, SB1 and switch SC1 has same gating signals. That means we can merge these three legs and then we can have a converter solution. That solution is shown here. So in this solution, in the DC side converter, instead of three edge bridges, we will have only 2 edge bridges, you can see. And you can see here total number of active switches reduced from 12 to 8. Now this change in the DC side converter structure has an impact on soft switching. Let us see what happens here. So in the bottom, what you are seeing are the pole current waveforms. Of this top one is the pole current waveform of red leg, and bottom one is the pole current waveform of this black leg. So basically, the pole currents are high frequency square wave whose magnitude varies sinusoidally over line cycle. So you can see the red leg has waveforms which, as professor has mentioned earlier, that near zero crossing magnitude goes below the GVS limit. So in this shaded, black shaded region, the red leg will be hard switched. For green and blue legs also, we will have similar envelope where the zero crossings will be 120-degree phase shifted. So these three legs will be hard switched in certain zone of a line cycle. But if you see the pole current envelope of the reference leg or black leg, you can see here this leg never touches, the envelope never touches the GVS limit, which is VDC by Z dot, as professor has mentioned earlier. So that means throughout the line cycle, it is possible to achieve zero voltage switching. So that means we have improvement in number of switch count as well as GVS performance compared to the last topology. We can further improve the DC side converter, and that structure is shown here. So as you have seen previously, that here we had 4 half bridge legs, but we can have with a converter with 3 half bridge legs where the transformer primaries needs to be connected in delta. Now, if we consider leg A and B as a half bridge leg, and if you do the phase shift modulation that I explained just in the last slide, suppose the gating pulse of switch SB1 is phase shifted with respect to switch SA1, then we can apply a quasi square wave across AB, and that voltage is shown in red here. If the modulation phase shift between them is MATS by 2, so that will be the pulse width of the voltage AV. Similarly, if we consider the half bridge leg A and half bridge leg C to form a H bridge, and if we phase shift the gating signal of SC1 with respect to SA1 by MCTS by 2, then effectively we will apply a quasi square wave AC voltage across A and C, which is shown in blue. And in this case, the pulse width is MCTS by 2, where MA MCs are the modulation signals as shown in the right hand side, which are sinusoidally varying over line cycle. Now the voltage across terminal CB will be difference between the voltage VAB minus VAC. So this is happening as the transformers are connected in delta. So you can directly subtract from red waveform the blue waveform, and effectively you will get this green waveform. You can see the pulse width of this waveform is MA minus MCTS by 2. Now, if MB is the B phase modulation signal, if MB is equals to MA minus MC, then effectively we will successfully generate the balanced three-phase output voltage. But one important thing to notice here that MA, MB, MCs are sinusoidally varying signals over line cycle, and this picture is true in the blue shaded region where MA is maximum, MB and MC are the mid and minimum values. And you can see due to their nature, mid and minimum value, M mid and M mean results in M max. So in this case, from this equation, you can see MB is MA minus MC. But it is not true in other regions of the line cycle. So what we need to do, basically in this case, we have considered A as the reference leg. So to implement similar modulation strategy, we have to change the reference leg after every 60 degree. And that change is shown here in the bottom table. So this is the full picture of this improved converter structure. The DC side converter configuration, as we have changed, it has also impacts its sub-switching performance. Let us see what happens. In the bottom, the top waveform is the current envelope of the transformer winding. But if you see the A leg pole current envelope, that is shown at the bottom. And you can see here the current envelope never touches the GVS limit, which is VDC by Z0. It is always above this limit, and which effectively helps to achieve GVS throughout the line cycle. Now for B and C phase current to envelope, if we draw, it will be like 120 degree phase shifted with respect to A, because we have implemented exact same modulation strategy like A. So effectively all the three legs will have complete GVS throughout the line cycle. So a half bridge leg is a basic building block of any converter. In our lab, we have developed a half bridge module using one IGBT module from Semicron, which is mounted on this heatsink. We have used a power PCB. Basically, these terminals are for DC connection and to connect to any other half bridge module for the DC bus. We have also developed gate driver circuits, voltage and current sensor circuits. Such a modular plug and play arrangement is easy to probe, debug, repair and replace. Not only this kind of arrangement can be seamlessly electrically and mechanically integrate to realize any complex converter architecture. Here each module rating is we can do around 10 kilowatt process to 10 kilowatt power to process through this module with 800 volt DC bus, and it can generate 415 volt AC 50 Hz AC. The switch can be switched up to 20 kilohertz. This we have developed with our colleagues in our lab. Bala, Shayan, Shoham has helped us to develop this. Using that half bridge module, you have seen in our last slide, we have implemented one of the converter topology that we have shown you earlier. In the DC side, we had 6 half bridge legs. Those legs are connected. You can see those terminals, small strip, little green color DC bus strip that are connected together to build a continuous DC bus. This is the high frequency transformer, which is rated for 3 kilowatt. And then the secondary side, we have the diode bridge and half bridge legs. To control the hardware, we have used Zinc Zinc SoC from Xilinx, which has dual Cortex ARM processor as well as FPGA fabric. Our concept is like this. We have a launchpad. Basically, this launchpad contains the SoC and some power processing circuit, and also clock and a few communication circuitry to just keep the IC alive. It is kind of a brain kind of a structure. We have we will have another board which is kind of a launch pad, because launch pad and which will have another board which will be the interface card. Launchpad and interface card, this module brings the flexibility in the design. This board, what you can see here, is basically a 7-layer PCB that hosts 400 pin BGA Zinc package plus necessary power supply, clock and communication related circuitry. Mihir, Shayan and myself were involved in development is this platform. This bottom green platform, what you are seeing, is basically the interface card. Interface card is connection between the launchpad and the actual converter. So interface card house mostly ADCs, DACs, and also signal conditioning circuitry, several optical transmitter and receiver ICs. So basically, this is a very strong control platform overall, which has 40 optical PWM outputs and around 18 ADC inputs. So basically, this platform can be used to control any complex power converter circuitry. So using that converter control platform, we have and you have seen the power hardware already. We have developed our hardware circuitry, and here what you can see the few experimental results. So on the left you can see the line voltage and line current waveforms. So top one, this what I am showing you is the line phase A voltage VAN, and the light blue color waveform is the phase A current. You can see here both voltage and current are in phase. So basically the operation is happening at unity power factor, and you can see the other phase currents are phase shifted by 120 degree. On the right hand side, what you can see are the some switching voltage and pole current waveforms. Particularly, I want to mention here, you can see the bottom two green waveforms. So one green waveform, actually the transformer primary current waveform, and the next one is the pole current waveform. We have already seen the current envelopes analytically that we have I have described previously. Those envelopes are shown here. As Professor has explained earlier, the subswitching process, that process is also experimentally verified, and that picture is shown in this slide. You can see this is the moment when we have turned off the switch S and the capacitor across the switch S starts charging. And the primary current IP, as Professor has mentioned earlier, that it starts ringing with the transformer leakage inductance and device capacitances, and it starts changing or falling. You can see this pink color waveform is the analytical current waveform, and here experimental obtained value. In that pink color waveform, it started falling sinusoidally. Now the voltage across the device is V, which is this red color waveform. And here actually we have connected the probe in the opposite direction. That's why I have mentioned it -V. So basically this is the voltage across the device. Gradually the current IP charges the capacitor across the device. So V actually builds up. And when V reaches VDC, it is actually clamped to VDC because the bottom diode will be forward biased. So in this zone, the primary current is sufficient enough to completely discharge the top device capacitance, completely charge the top device capacitance and discharge the bottom device capacitance. And after that, when the diode will conduct, we have applied the bottom device to getting pulse to the bottom device, which results in GVS turn on of the bottom device. Now in our lab, we have only developed the power converters up to 6 kilowatt, but our target application is utility scale, probably few hundreds of kilowatt converter. So what we have done effectively in our lab, we after building the converter, we have tested the converters and we have also calculated the converter loss analytically, and that analytical estimation is verified from the experimentally obtained value. So you can see here the experimental and analytical loss values are closely matched. So using this same analytical approach that we have verified in our laboratory prototype, we have used basically theoretical design for 200 kilowatt converter with 800 volt DC input and 415 volt 50 hertz AC output, and we use same analytical approach to estimate the converter power loss. Also, we have done the same thing for a conventional solution as shown on the right. Interestingly, we have found that the loss in the semiconductor of the proposed topology and the conventional solution are pretty much close. There is another interesting idea I just want to mention here. Till now, what we have seen, we have 3 pulsating DC links for 3 phases. In the pulsating DC links, so basically what we have pulse width modulated DC voltages, and where the average is this sinusoids, rectified sinusoid. Then after the DC link, we are using a line frequency switched edge bridge to generate the line cycle AC. So for 3 phases, this rectified line voltage are phase shifted. So we need 3 such DC links to generate 3 phase waveforms. Can we reduce the number of DC links? So interestingly, we have found one method which we have used here. So in the bottom, what you are seeing here are the 3 line voltages, VAB, VBC and VCA. So in the shaded region here, let us consider the shaded region, pi by 3 to 2 pi by 3 zone. Here you can see VAB is the maximum and VBC and VCA are minimum and medium values. So if we consider their rectified waveforms of VBC and VCA, those are shown in green and blue color. Now previously also we have seen, if we add, due to their nature of this sinusoid, if we add medium and minimum values, it will give the maximum value. So this idea we have used here. Basically the blue signal what you are seeing here is the voltage across AC, VAC in this zone, and the green one is voltage across CB. So now if we use a switching network like this, where in the DC port we have generated these voltages, and we turn on the switches like this. A is directly connected to the to this top DC port where we have A, and C is connected, black line is connected to the middle, and green line is connected to the lower DC port. So basically we will be applying the required AC voltages across the poles. This process can be repeated in other sectors of the line cycle. So in this way, we can have a successful modulation strategy. We can have a converter, and particularly if you notice here, during this whole duration, these switches are not switching. So basically, this particular switching network will be a low frequency switching network. So though it looks complicated, but you can see here, using the same concept, we have two additional topologies, where in the right hand side, the same 3-level structure is used. These two diode bridges and the primary side converter is used to generate the required DC as shown here. In this case, in the second case, instead of 2-level, we have 3-level legs. The details of these converters are available in this publication. Now I want to hand over Professor Basu to summarize this talk.
Oh, thank you, Anirban. I will. You need to mute and stop sharing. I will. So, do you see my screen, Anirban?
Yes, sir.
Okay. So, Anirban, thank you very much. So, I think we are ready to close this. So, here is a summary of what we have learned so far. There are so many things we talked about, but this is the story, right? So, what is the background? Background is we are looking at the utility scale grid integration of solar and wind, right? That is a megawatt level, and which involves, in all the cases, a DC to AC converter, which is a 3-phase inverter, the regular 3-phase inverter, followed by a line frequency or 50 or 60 hertz transformer. The solution is highly efficient. With IGBT at a 500 kilowatt, you can achieve a peak efficiency of about close to 97%. But it has this low frequency transformer, which is huge and the heaviest component in the entire system, which we do not like. Now, we know that it's possible to reduce the size of the transformer by increasing the switching frequency. And this is the trend in all of power electronics, which is evolving from 1970s, that increase the switching frequency and you reduce the size, right? So now the problem is, if you introduce a high frequency transformer, that requires complex converters, because remember, the frequency at the grid is only 50 hertz. So, but now if you use complex converters, it will increase complexity, it will bring in more devices, and that will lead to higher power loss. And that is the reason why we do not see this kind of concepts, though this is around for a long time, has been actually implemented and successful converters are being built. So what we did is through innovations in topology. So topology means converter configuration, how the network of the switches are connected between the DC and the AC port, and switching strategy, like how you're going to turn on, turn off these devices that you are in your converter. That is called soft, and the switching strategy or the modulation strategy, we achieved soft switching and line frequency unfolding. So this tells us, with this converter topology, actually we have been able to decouple the switching loss that is happening in the devices with the frequency. So now you can simply keep increasing the frequency and reduce and improve your power density. So that's a fantastic thing. But let us don't forget, the losses in the magnetics are also functions of frequency. So if you increase the switching frequency, it does not mean that the losses are going to always decoupled. But of course, this shows it shows that it is possible actually to achieve a similar ballpark efficiency with the state-of-the-art solution, right? And remember, we are only talking about IGBT-based solutions here. So if we use wide bandgap-based silicon carbide solutions, we can actually achieve phenomenal efficiencies in this kind of circuits. So it has a lot of promise in it. That is what we see. And we are in the lab going to build a bigger power converter of the actual size, right? So that's work is now in progress. The limitations, yes, there are big limitations here. So one thing is that you see that the complete line frequency switching that we achieved in the AC side converter is because of the diodes, right? Now the diodes simply did the rectification, but this results in UPF operation. Now, UPF operation is a beautiful thing, right? We always want UPF operation. For when you want to transport a given amount of power, you want the power factor to be unity. That is the best case. Why? Because if you have reactive power, your effective current will go high, which will mean higher losses. And if you have more reactive power, it will change your voltage in the power system, right? So people like UPF. And to the best of my knowledge, most of the grid-tied inverters today are still operated in the zero power at unity power factor, right? Because reactive power, if you add, it will eat into your rating of the converter, right? So, but the thing is that because now you have a higher penetration of renewables into the grid, now you need to provide reactive power support because you are now capable with this renewable generation to change the voltage profile of your power system. So like what happens with other synchronous generators, the grid may ask you to now provide some reactive power. Now these converters, the way they are, because of the diodes, cannot provide you that, right? So this is one of the major limitation, and we are working to see that, how can we improve over that. And then finally, that something we have really pushed under the carpet, because we all know this work is based on phase shifted full bridge and PWM converters, right? And we know that phase shifted full bridge has this problem of voltage overshoot in the secondary because of the parasitic capacitances which are present in the diodes, and which causes ringing and all that. And you need active snubber circuitry there. Now, we are also working on this with a few of my students are working on this to find out a solution, that can solve, though this is an age-old problem. A lot of people in the industry knows this problem, but still we love our PWM converters because they are essentially independent of load and easy to control. And that is why all the DC-AC inverters, which are there in the grid-connected systems, are PWM converters, right? You can change to PWM converter. You can go to dual active bridge or resonant based, where you can achieve, you can solve this problem, but we will lose this beautiful thing about PWM converters in this case. So we are trying to work around the solutions. So these are civil limitations and future work. And so we have come to an end. So I would like to acknowledge a few grants which made it possible to do this work. So we got this IISc startup grant when I joined, very handsome grant that I got. And then Early Career Research Award from Science and Engineering Research Board, Department of Science and Technology. And then the microgrid project, which actually Professor Vinod John was the PI. And he also generously let us use the funds to build many of these converters. And finally, for this talk, I would like to thank IEEE Power Electronics Society Bangalore chapter for organizing this beautiful event, particularly Dr. Prema from BMS College of Engineering and Mr. Hari Krishnan from Digits. So that is our IT backbone of our institute. And I really thank all of you for your patience. And here are people who have funded us. So now we thank you, and we are ready for questions. Thank you for your patience.
Yes, sir. Thank you, sir. Thank you for such an informative webinar, such an informative talk. We have a lot of questions, and there's a question from Professor S.K. Vishwas. I think you have answered the question already. I'll read out the question. Will the scheme work for non-unity of power factor AC line current, as there is no path for circulation of reactive power in DC bus? So just now you had answered. I feel the question is well answered.
Thank you, Professor. I think you got it right. Yes.
And there is one question from Professor Tukaram. Typical 100 MV solar plant, what will be the cost of this power electronics scheme?
So I think this is a very good question. And the thing is that we at the university do not look at the cost, right? We are just trying to find out a better solution which can perform better. So we have not done any cost analysis, but you can see that if we are looking at, we are trying to replace the line frequency transformer and the inverter, right, with this solution that we talked about. And certainly this solution has larger number of switches, right? So, but remember, again, the switches are more in number, but they also distribute power, right? The power, effective power rating of the devices are not going to be same, are going to be similar as the conventional solution. But certainly this is going to be more expensive at the first. But once we deploy and we actually make successful converter, then probably as we can penetrate into the industry, the cost picture will change, right? And about the high frequency transformer of a similar rating of a few hundreds of kilowatt, how that will compare with a regular low frequency transformer, my simple answer is I do not know, but they shown to have a similar loss spectrum, at least from the performance wise. I think they would still be comparable. Okay, thank you.
Okay, sir, thank you. There is another question from Shiladri Chakrabarti, that is, do the diodes in the proposed topologies exhibit turn-off voltage spikes on account of leakage inductance of the transformer?
Okay, I think this is a good question, but what happens is that the way we are controlling, right, the turn-off spike will not be seen in this topologies. Right, if you look at the soft switching procedure or how the switching is done, that is typically seen in the hard switched converters. That may not be seen here, and it will not be seen here. And the good thing is the turn off of the diodes, right? They are, so the thing is that the turn off or the reverse recovery, right, of the diode is a function of how fast the current in the diode is dying, right? And you see, because of this inductor, the speed at which current will be coming down across those diodes is a function of those inductors, right? So they will actually slow it down. So the reverse recovery effect will be lower in this kind of topologies. But again, I said this, the other effect, right? Once the diode is turned off, it will become a capacitor and it will start oscillating. That I did not tell you guys, and I pushed it into the rug. But if you're familiar with that, I know you are, full bridge converters, you know that that's a serious problem, right? So that problem I indicated in the conclusion, right?
Yes.
And you need snubber circuits for that. Yeah. Thank you.
And how do the transformer sizes of and VA ratings of topologies on slides 14 and 15 compare?
So if we go to 14 and 15, let us take a look at. Okay, so I see that 14 and 15. I think maybe I will pass on this question to Anirban. Can you answer?
Yes, actually, Professor, you can, yes, the screen is here. So 14 and 15, basically, if you see the transformer voltage profile and current profile, they are exactly same. They doesn't, from the transformer perspective, they doesn't see any different terminal voltage or current through the transformer windings. So in my opinion, there will be no difference in transformer size between these two topologies. But though the DC side bridge, the difference is in the DC side bridge, the switches in the DC side bridges. So basically there will be the current sharing between the legs will be different. And yes, in I think 15, the topology, the reference leg will have higher current compared to the legs in the slide 14. So that's my answer. Thank you.
Okay, thank you. There is another question from slide 24. From the efficiency curve, it seems that the efficiency is around 94% if the converter is soft switched. Then from where the large losses are coming?
Professor, should I answer this?
Yes, yes, please go ahead. Yes. This is the
So
reverse question.
yes, exactly. When actually when we are giving this, we have also mentioned this thing. So basically, what you are seeing here, yes, the losses in our topology, what we have built in our lab, is not optimized. So basically, in this, in our topology, in our prototype, we have used high voltage blocking devices. The applications here, we are in the test, we have used 400 volt DC, but in actual cases we have used it was 1200 volt DC bus, 1200 volt devices. So devices were not optimized, and also many other components used in the circuit were not optimized, designed for a particular power rating, for the power rating that we have done the test. So that is the major and main reason why we have seen some amount of loss in the DC side bridge. Other components also includes like magnetics. Those magnetics, the loss in the magnetics is also contribute to the loss here. So this is also another research direction where we can improve the magnetic design in the magnetics such that we can have reduced loss. Thank you.
Okay, thank you, Dr. Anirban. So I think we have taken almost all the questions now.
Okay.
Yes, sir. On behalf of IEEE PELS and IES chapter, I'd like to extend my sincere thanks to Dr. Kaushik Basu and Dr. Anirban for accepting our request and setting aside your precious time and effort to deliver such an informative webinar. Thank you, sir. Thank you very much. And I'd also like to thank Harikrishnan, sir, to help us setting up the Teams live meet. My sincere gratitude to all the participants to join the event. Thank you very much. And sir, many participants are asking whether we can share the recording of the session.
Sure, madam. What we can do is we can download the recording. Mr. Harikrishnan will help us, and then we can actually upload it in YouTube, and then we can share the link.
Sure, sir. We'll do that.
Okay. Sure. Thank you, madam.
Thank you, sir.
Thank you, madam.
Thank you, everyone. Once again, thank you.
Thank you, everyone. Thank you, Anirban. Thank you,
Thank
madam.
you, everyone.
Thank you.
Sir,
Thank you. Have a very good night, a very good day, and very good afternoon, wherever you are. Thank you for your patience. Okay. Bye-bye. Take care. Stay safe.
Bye-bye.
Bye-bye.